Welcome. Today I am going to start the next reducing reagent, that is Gilman reagents. Before I start the class, previous class I talk about of that Gilman reagents. So basically what we have completed now, first we talk about of that hydrate transfer reducing reagents. Hydrate transfer reducing reagents. Over here what we have talked, that we have talked like lithium aluminum hydrates and NaBH4, divalate and L or K electrolytes. These things we have discussed on that hydrate transfer reducing reagents. Now another types of reducing reagent, that is carbon transfer reducing reagents, means that is carbon that have the negative charge. So I can say that carbon transfer reducing reagents, it means that will be have something like C minus will be there, and that will transfer here. So this type of reagents are what you see that first is we talk about of Grignard reagents. Here what we will see that like then any alkyl groups, this R minus will transfer and that will do the reactions. Here what was used to that reacting conditions, here H minus used to go. Okay, so now here that like Grignard reagents, or we can say that we will discuss today I'm going to discuss about that Gilman reagents. This one also called that organocuprate reagents. Organocuprate reagents. And another things we will discuss in the next class, that is alkyl lithium reagents. Alkyl lithium reagents. So all these things here that R minus will transfer. Okay, so in this case H minus will transfer and that will do the reactions, means that will help to reduce the reactions of the substrate. And for this case carbon transfer reducing reagent, on this case R minus will go and that will react and that helps to reduce the substrate. Okay, so that things we will discuss today. So previous class I have already discussed about of that Grignard reagents, where it will do the reactions and what that solvents is needed. Okay, that I have discussed in the previous class. Now I am going to discuss about the Gilman reagents, and in next class we will discuss about of this alkyl lithium reagents. So for that Gilman reagents, this is also called that organocuprate reagents. Okay, on this organocuprate reagents, what we say that this is generally R2CuLi. Okay, so this is that general formula of organocuprate reagents, where copper will be there with that R2Cu and Li. This will be there, that formula of organocuprate reagent, means lithium will be there and copper will be there, and with that this R can be RH any alkyl group, or it may be that it may be that is maybe that cyclic, or it may be that acyclic. This may be that cyclic or can be that acyclic. Okay, so this is about of that organocuprate reagents, and how it is will be there, that we say that this is R and this R2 and Cu and Li, and the negative charge will be on this carbon, because almost all that metals are give the positive charge with respect to that carbon. So this will have that positive charge. So this R2 will be do the reactions. Okay, so that is about of this reacting part of this organocuprate reagents. Now whenever I says that any reagents, like you see that this mainly these organolithium reagents, we will do that comparisons with that Grignard reagents. So what you used to study in the Grignard reagents? Grignard reagents, bosses, I can say that is that organocuprate reagents or Gilman reagents. What things we will do that here, that Grignard reagent and Gilman reagents. So in case of Grignard reagents, if we have this type of bonds, like if we have this carbonyl groups, okay, now if you are attacking to this with a this Grignard reagent, let's say that CH3MgBr, this is a Grignard reagent. If you attack it, then what it will do, that it has that this all this carbon transfer reducing reagent, this has that carbon has the negative charge, and that is going to attack here. So this is going to attack here, and this is going to do that, and we see that this is a hard part, and this is hard, and this is also hard. So hard has a good interaction. So here what we say that 1-2 direct additions will occur. Okay, so that we have discussed in the previous class. Now if the same case, if we do with that Gilman reagents, same case, if we give these types of carbonyl groups, now if we are going to attack that R2CuLi, then what will happen here, that this will not react here, this will not happen. It means that we will get that no reactions. Okay, it means that it gives some interesting comparison between the Grignard reagent and Gilman reagents, where that Grignard reagents will attack to it, but the Gilman reagents not attack to this carbonyl groups. Okay, then where it will attack? So if you change little bit to this, then the Gilman reagent will attack. So the little bit change means that if you have this type of groups, and let's say if we have another groups, and here we have that double bond, that means that to this carbonyl group, if a conjugations will be there, on that case here if you give this Gilman reagent, that Grignard reagent CH3MgBr, then it will attack again at that these positions. But now if you give these things to this Gilman reagents, then what will do here, if it is there, now you are going to give this Gilman reagents R2CuLi. Now what will do, this Gilman reagent, this has that negative charge, so this negative charge, it means that here this R minus is there, and this will attack to this carbon center, and this will do this. It means that this will do that 1 for conjugate additions, it will do that 1 for conjugate additions, that I have discussed in the previous class, that acid base HSB principles, that this become a soft here, and because this is a soft, and this will attack to this soft part, and we know that this is a hard part and this is the soft part. And why it become a soft part, reason is that here the copper is there, and copper has a high size, so that makes the whole reagent as a soft, and it will attack to this soft part. It means that 1 for conjugate additions will occur. Okay, what I said in the previous class, that this become 1 and this will become 2 and this is 3 and this will become 4, means that 1 for conjugate additions will occur. Okay, and what happened, that this double bond will shift here, and this will go to like this, means what will get that answers, let's say here we will get that O minus, and that is going to shift it here, and R will be attack here. But in this case, what we get here, in this case, that is become O minus, and here we will get that another R, and that double bond become same as it is, it will remain intact. It means that this Gilman reagent react to these carbonyl groups if it has a conjugate double bonds. On that case only this Gilman reagent will work. If that simply a carbonyl group is there, on that case that Gilman reagents will do no reactions. Okay, so that is that important points about of this Gilman reagent and Grignard reagents. So this Grignard reagent that I have discussed in the previous class, that it will do that 1-2 direct additions, Whereas this Gilman reagent, it will do that 1,4 conjugate additions. If simply a carbonyl group is there, then on that case, Gilman reagents will do no reactions. So now the question is arise that whenever this double bond comes, then only this Gilman reagent do the reactions. So questions will be there that if we have that simply a double bonds, let's say any double bonds is there, this or any double bonds, let's say here double bond is there, whether now if I give that Gilman reagent, that is R2CuLi, or here if I give that R2CuLi, then whether that it will do reactions or not. So what it is found that here also it will do that no reactions. No reactions. It means it is clear that this Gilman reagents will do the reactions only if there is a conjugate double bond with a carbonyl groups. It means that to a carbonyl group, if a conjugate double bond is there, on that case only that Gilman reagent will do the reactions. Otherwise, if it is simply carbonyl groups, no reactions. If you give simply a isolated double bonds, then also no reactions. So this makes an interesting points to study about of this Gilman reagent, that if we have that conjugate carbonyl groups, then we can use that Gilman reagent where it will do that 1,4 conjugate addition reactions. Okay. So now the question is why it always do that the carbonyl groups, if it has a conjugate, then only it will do the reactions, otherwise it will not do the reactions. What is the reason behind it? So the reason is, what is found that, let's say if you have this type of groups, or let's say if you have these groups, now if it is a carbonyl groups and it has that double bond which is conjugate to this carbonyl groups, now in this case what we see that if you do that resonance, then what we look here, that this will shift it here because this is the electronegativity groups and this is going to shift like this. So from here what you see, that is going to like this, and this is going to be the negative charge, and here it is going to be like this. Okay, this is the one conjugate parts, and here also that what you see that since here this is a negative charge and this is a positive charge, so here also what you see that we can do like this also. This O is negative and this is, let's say, delta negatives, and this is delta positives, and this is that. And here after the conjugation, so after shifting, what you get here, that here delta positive charge you are getting, or here you are getting that positive charge. It means that so simply write here, this is negative charge and this is positive charge. So from these three conjugating resonance, this is one conjugating resonance, this is second, and this is third. So in this three conjugating structure, what you see that this positive negative charge is present either here and here now, and in this case here and here. It means that that positive charge means that what you say that this R2CuLi, it is a nucleophile, that is R minus, which will search for that electron deficient groups, and electron deficient groups is arising where that is first is here, another is here. Okay, so now this R2 will since this is due to this copper, this become a that soft center, so this will attack to this carbonyl center, it will not attack to this carbonyl centers. That is the reasons that if a carbonyl groups, if it is conjugations, then only it will do the reactions. If it has that simply this type of bonds, let's say double bonds, on that case it will not do, because here what we see that this here the, let's say here positive and here if you that here if it is positive and here negative, here there is no any conjugations, means this carbon center is not so stable, or you can write here positive, here negative, so this carbon center is not stable. Or if it is like this is also not stable. But you see that this carbon center is stable due to that conjugations, but this positive carbon is stable due to conjugations. But now in this carbocations, it is not stable because there is no such any here we not get any that type of conjugations. That's why this alkyl that Gilman reagents that will attack only to this type of groups where that carbonyl group is there with conjugate with that a conjugate double bond is there, then only that will do the reactions, otherwise that will not do the reactions. This is that one interesting things about of that Gilman reagents and that Grignard reagents where it will do that. And somehow like we see that sometimes that Grignard reagents do the reactions, but that Gilman reagents do not do the reactions. But if it has that conjugate carbonyl groups, on that case that Gilman reagent will do the reactions, and that also do that 1,4 conjugate additions. If that conjugate carbonyl group is there, Grignard reagent do the reactions, but it will do that 1,2 direct additions. Okay, so that is the difference between that Gilman reagent and Grignard reagent. So from here we will see that Gilman reagent will do that 1,4 conjugate additions. This is the first point of Gilman reagents. First point is that Gilman reagents added to carbonyl group having conjugate double bonds, and that what, and it will do 1,4 conjugate additions. Okay, this is about of that Gilman reagent first point. And second point, what we see that interesting things about of this Gilman reagents. The second point is that this Gilman reagents do a it give a SM2 reactions. It means that Gilman reagents give SM2 reactions. What we see that if we have that groups SN2 reactions, it means we know that if we have a carbon center, and if we have that any living groups, and if we have that like we have that H, and here we have that H, and here we have that any groups, let's say R is there. Now we are giving any nucleophile, because this is an electron deficient groups due to this living groups is there. And that now if you give me a nucleophile, then what happened, this nucleophile will do the backside attacks, and this living group will leave, and this will do the transition state will be transition state will occur here. Then it will do that means that at the same times both nucleophile will attack, and at the same time the living group will leave. That is called that SN2 reactions. And for this case, that nucleophile should be a strong, because that nucleophile will be that first approach that it will do the reactions. First nucleophile will attack, and then living group will leave, means that it will happen at simultaneously. Whereas for SN1 reactions, what will happen, that for SN1 reactions first living group will leave. Let's say here we have R, here we have R, and here we have, and here we have that living group. So for SN1 reactions, first living group will leave. Then what happened, that this carbon center has that positive charge. It means that this is a highly electron file, and now any that nucleophile, it may be good nucleophile, it may be bad nucleophile, that will attack here, and it will attack here, and that this will add it to the same site where that living group will be. It means that if living group will be this site, then the nucleophile will come to that same site. That means living group and nucleophile will be come to the same site as the living groups. So this is called that SN1 reaction. Whereas for SN2 reactions, what will happen, that that living group will leave, and that nucleophile attack, to the backside of the leaving groups. That is called that SN2 reactions. Okay, so for this case, that leaving groups and nucleophile that will add means comes to this reactant at the same times. Means same times both attacking of nucleophile and the leaving of the leaving group will be happen. It means that nucleophile should be a strong. So what we see that for case of Gilman reagents, it will give a good SN2 reactions. It means that if you have that groups like, so what we see that this thing is also important, but for SN2 reactions, that order of that SN2 reactions is first will be the 1 degree, then 2 degree, then 3 degree. Okay, and for SN1 reactions, that order of that good SN1 reaction, that is first H to be 3 degree, then 2 degree, then 1 degree, but that is carbohydrate. Okay, so carbohydrate, if it is 3 degree, then that will give good SN1 reactions, and 2 degree, then 1 degree. But for the SN2 reactions, 1 degree, 2 degree, 3 degree. This is about of that SN1 and SN2 reactions. So why I am talking about of it? Because the Gilman reagent will give good SN2 reactions. It means that if it is a like this type of groups, if we have this carbon, and let's say we have that H here, and H here, and here let's say we have that leaving groups, let's say we have that chlorine. Okay, now we are giving a Gilman reagents, that is R2CuLi. So this is actually gives that R minus. Okay, now this R minus will attack to the back side of that, because it will going to give that good SN2 reactions. It means that they will attack to here, and that leaving group will leave. Okay, it means that what we get here, C H H, and this is R, and yes, so this is going to be the R, and this is going to be the H. Okay, so this R will come to the back side of the leaving groups. Okay, so this is that SN2 reactions. Now what we seen here, that for case of that the type of Grignard reagent, that SN2 reactions will not give. Means that contradictory will be that if you have that Grignard reagents, and you have that Gilman reagents, okay, so now here we want to do that SN2 reactions. Let's say we have that groups Br is there, and we are going to give that CH3 and GBr. Okay, and the same things we have here Br, and we are going to give that Gilman reagent, that is R2CuLi. Note that here we are getting that R minus, here also we are getting that R minus. Okay, now the difference is that this R minus, where we are getting that this is a good nucleophile. That's why it will going to give a SN2 reactions, but it is not so good, not so good nucleophile. So what we say that for SN2 reactions, that nucleophile should be good, then only that is going to give the SN2 reactions. So here what we see that here we will not get that SN2 reactions. So no SN2 reactions. Why? Because here that instead of happening SN2 reactions, it will happen some like protonations or deprotonations that will happen, or reductions will happen. So that things will happen instead of happening SN2 reactions. But in this, that R2CuLi, since this is a good nucleophile, this R minus, this what will do that this will attack here, and this is going to get like this. It means that let's say if we have this type of groups, let's say I am going to give here is copper is there, and here this is there. Okay, so now what will do that from here, what will get here, that this group you will get, so this will attack to here, and this is going to leave. So here we are going to get this and this. It means that what we say that this is the SN2 reactions, because that leaving group, this nucleophile attacking backside, and the leaving group is leaving. Okay, so this type of groups you are getting here, or just for that we will discuss later. Just for simplification, so you have that R2. Okay, so now if we give this, then what we will get here, this, and here we have that R group. Okay, so this is a good SN2 reactions. So whereas that this Grignard reagents will not do a SN2 reactions, but this Gilman reagents will do a good SN2 reactions. So for this Gilman reagents, it helps Gilman reagents helps to form carbon-carbon bonds. Means that if you want to form a new carbon-carbon bonds, then Gilman reagent is a very good option. Like if we have this type of groups, okay, here we have that Br, and now we are going to give that this type of Gilman reagents. Let's say we have that copper, and like this 1 2 3 1 2 3. We want to add this chain. You want to increase that chain. So what you will do that? You will do that Gilman reagent. This is the same form as like R2CuLi. Okay, here this is plus, and let's say we have that Li is there. So from here overall what we get that 1 2 3. So overall we are going to get this groups. Okay, so this will attack to this, and this is going to live here. So what we get that 1 2 1 2 3 1 2 3. Okay, and then this again 1 2 3. This is 1 2 3. Okay, 1 2 3. So this comes from here, and this will attack to this. So again another 1 2 3 bond will form. So it means that it forms a chain, carbon-carbon chain. It means that it has to form a new carbon-carbon bonds. So whenever we have to increase the chain, carbon-carbon chain, then on that times it is a very good option to take that Gilman reagents. That will help to give you this types of forming new carbon-carbon bonds. Okay, and this is a one type of SN2 reactions. So on that case, we can use the Gilman reagents to form that carbon-carbon chain, or this to form that new carbon-carbon bonds. So if you have to increase the chain, on that times it is a good option to take that Gilman reagents. So this is the next useful of taking the Gilman reagents. Okay. So what is seen here, that second useful of that Gilman reagent is to form new carbon-carbon bonds. Gilman reagents that's good useful. Or I can say Gilman reagents helps to form new carbon-carbon bonds. Okay, so this is the second useful of this Gilman reagents, and the third useful of that Gilman reagent is that I say that the functions, that is like we have seen that a carbonyl groups with that it leaving group is there, and we are giving a Grignard reagents. Let's say we have that type of groups like acid chloride. Okay, Cl is there. Now we are going to give that Grignard reagents. Okay, and now here we enter the Gilman reagents. So basically that Gilman reagents, that is that just contradictory of that Grignard reagents. It means that it will give a opposite competitions of that Grignard reagents. So if you have that Gilman reagents, then what you will do that? Here if we are going to give the Grignard reagent, let's say RMgX, and here Gilman reagents, let's say that RCOCl is there, and you are going to give that R2CuLi, then what it will do that this give the negative charge, and it will attack to here, and it is going to like this, and it will return back, and this is leaving group will leave. It means that RCO and R you will get. Now this is add once. Now we see that this Grignard reagent again it can attack to that ketone also, because it is a hard, and it will attack to that hard center. Again we have that hard center, so again this RMgX will attack, that I have discussed in the Grignard reagent cases. This again it attack. Okay, now it will do that nucleophile addition reactions. It means that RCO minus, and here will be R, and here it will be R. So this will get that, it means that if you after hydrolysis it will go to that OH. So here we are getting that 3-degree alcohol. So for that Grignard reagents, what we see that we adding that Grignard reagent twice for the case of that alkyl group, carbonyl groups if have the leaving groups. But now if we are going to give these kinds of that Gilman reagents, what it will do that in this case here also you get that R minus, and now since here leaving group is there, in this case although this is a soft reagent, but again it can attack to these groups, and this 1-2 additions can happen here in this case, that if you have that leaving groups, what will happen that this will go into like this and this come here and the leaving group will leave. It means that RCOR means up to ketone it will do that, but after that that Gilman reagents will not work, then no reactions. Okay, it means that the Gilman reagents, if we have that like chlorine, that acid chloride is there, then the Gilman reagents can do that this carbonyl group, it can attack to this carbonyl group, but that will do once. After that leaving group will leave, it will leave up to ketone only. Okay, so ketone will form. But for the case of Grignards, it will do after that also will reduce to the 3-degree alcohols, but it will reduce up to the ketones. Okay, so these are the basic points regarding of that Gilman reagents and that of that Grignard reagents. Okay, so if this is acid chloride, or if it is having that kinds of OCS3, then also if we give that, then this is a good leaving groups. Here also what we see that if we going to give R2CuLi, it can attack again here, and this is going to like this, and this is going to give this. Here also we will get that ketones. Okay, similarly if it is like this, and if we have that anhydride also, RCO and COCS3 anhydride is there, then also if we're going to give that R2CuL, then again it will attack here, and this is going to leave, and this is going to again we will get that ketone. So if that leaving groups is there, on that times this Gilman reagent can attack to these carbonyl groups, and we will comes to a ketone part. But for case of Grignard reagents, it will reduce up to that 3-degree alcohols. Okay, so these are the basic usefuls about of that Gilman reagents, and the basic difference between the Grignard reagent and the Gilman reagents. So what things we have to remember for that Gilman reagents? First, it will do that it will not attack to the ketones. It will do not able to react with isolated ketones. Okay, it means that this is there, and you are going to give that R2CuLi, then we will give that no reactions. But if you have that conjugate is there, and then you are going to give that R2CuLi, then it will do that one for conjugate additions. Okay, and you will get that this type of products. Okay, that we will discuss. This is the first point. And secondly, what will do that Gilman reagents give SN2 reactions. Okay, it means that forming new CC bond. Okay, and third, it adds to acid chloride once, whereas Grignard twice. Okay, so these are the basic things we have to remember for that case of Gilman's reagents. Okay, now we'll do that question answers to clarify more about the Gilman reagent, how it will do the reactions. So moving to the question answers. Okay, so first example is we have this type of epoxides. Okay, now we are going to give that Gilman reagent, then what it will do. So see here that M2Cu alive. Okay, so this is a one that is organocooperate, that is Gilman reagents. From here what you will get, that CH3 minus. Okay, and this will attack to where, that it will always do that 1,4 conjugate additions. If it is epoxides or it may be any other groups, if that 1,4 conjugate addition is there, then it will attack to here, it will not attack to these groups. Okay, so what it will do, that it will attack to here. Okay, and it will move to here, it will move to here, and this is going to be break. Okay, so just name it, let's say it is 1 2, this is 3, and this is 4, and this is 5. Okay, so what will do, that this CH3 will comes here, it means that this is 1, and here we have that CH3 groups, and 2 3 is going to get that double bonds. So this is 1, this is 2, and this is 3, 2 3 get double bonds, and what will happen, that this 3 4 will going to break, 3 4 will be going to break, and 3 5 will be that this is 3, and this is going to be that 5 and 5, then here we have that 4, and 4 here we have that oxygen groups. Okay, so this is going to happen. So to if get the confusion, then always make this naming, that will going to help you. Okay, so this is going to be the answers, and this is going to be that O minus, and that they did hydrolysis, then here that H will come. Okay, so this is the final answers for this question. So whenever you confuse about of that rings, or about of that how many carbons are there on the times, just name it and you will do that, you will get the correct answers. So moving to the next questions. In this case, again we have that Gilman reagents. So again we hear that Me means we are going to get that CH3 minus, and where it will attack, so it will always do that 1,4 conjugate additions. If it is a carbonyl groups, or if it is any living groups is there. Okay, so that should be, that's why I'm giving more and more examples, that from examples you will clear more, that if it is a carbonyl groups, or if it have that any living groups, then also it will do what, that 1,4 conjugate additions will do. Okay, it will attack to this, it will go into that, and this living group is going to live here. Okay, so not only a carbonyl groups, if you have that any living groups, on that time also it will do that 1,4 conjugate additions, that reactions will happen and it will do that 1,4 conjugate additions. So what we will get that answers here, that is going to be like this. Okay, living group has lived, and this is going to be the double bonds, and here we have that one CH3 and another CH3 will be here. Okay, so if that stereochemistry is mentioned, then you see that one is above, then other has to be below. Let's say here one is CH3, then other has to be that above. Okay, and now it is attack here, and that living group has lived. So this is the final answers for these questions. Okay, so from here what we see, that on not only carbonyl groups, if that any living group is present, then also this cooperate reagent, that is Gilman reagents, attack here, and it will do always that 1,4 conjugate additions. Okay, now moving to the next questions. For this also we will get that CH3 minus. Okay, and what it will do, that it also again do that 1,4 conjugate additions. Here that carbonyl group is there. Previously in this case what was there, that a living group was there. So either living groups or this carbonyl groups is present, on that case this will attack to that, it will do that 1,4 conjugate additions. So now what will do, that it will attack to here, and it is going to be there, and it is going to be here. But now the question is what, that here that stereochemistry is mentioned here. It means that, remember that whenever in a questions that one side that if it is a single ring and substituent is stereochemistry is mentioned. Okay, so I will write here, if in single if in single ring, okay, I'm saying about a single ring, okay, adjacent the incoming group attack opposite to stereochemistry of adjacent substituent. Okay, this is the points what it says, this point. This is very important, so you have to remember this, that if in a single ring, so first look that that has to be in a single ring, the incoming group means that here that this is the incoming group attack to the opposite to the stereochemistry of adjacent substrate which is already present, okay, which already present. So this is already present substituent, so this incoming group will attack opposite to this, okay. So if you are confused, then we can make also that into the chair form, okay. So now if you see here actually this for the memorize, that if you don't want to memorize, then just convert into the chair form. So here if you have these carbonyl groups, and let's say here 1 2 3, so here you have that double bonds, and here this is in the above, okay. So that incoming group will attack where, so it will attack to that this ring, because this will do the 1 4 conjugate additions, and 1 2 3. So what we see here, that this CH3 minus, okay, so this is considered as a that it is considered as a bulky group. So and the bulky groups always do that equatorial attack to avoid that 1 4 conjugate additions, so it will attack to the equatorial positions. So here that equatorial positions is again that below sides, because above side is that this, so this will attack to the below side, so this is going to be O, and this is going to be that this side going to be that CS3, and here is the above side. So but you see that this is below side, so this is again going to be that here going to that below side. So if you don't want to memorize, then just remember that if single group, the incoming group attack opposite to the stereochemistry of the substituent group. So this substituent group which is already present, then that what the stereo is, it is above, so that incoming group will attack to that below side, because this is already in the above side, okay. Or if you don't want to memorize, just convert into that chair form. On that chair form, look that chair form, what you see that 1 3 axial interactions would not be present. So likewise we can attack, and always assume that only H minus is considered as a not bulky group, with that except that like CH3 all are assumed as a bulky group. So these bulky groups always attack that equatorial positions, okay. If they attack that axial position, then 1 3 diaxial interactions will be there. If there is no options that has to, that already group is present, on that case it has to attack axial position, because one group already in the equatorial positions, and that has to attack on that positions only. On that case it can do that axial attack, even if 1 3 diaxial interactions is going to happen, okay, because on that case there is no any options. But maximum times that whenever this bulky group is present, and that will maximum attacks in that equatorial positions to avoid that 1 3 diagonal interactions. So just if you don't want to memorize, don't want to look anything, then just remember that if in a single ring, the incoming group attack opposite to the stereochemistry of adjacent substituent which already present. So this is attack to that opposite to this. So what we do get here, this is going to attack here. So since this is already in the above, so this is going to be that below sides, okay, and this is shifted to here, and this is going to be that O minus. Okay, now if we do that hydrolysis, then what you see that OH bond, if that H will do here OH, and if it is going to be like this, and here it will make that CH, and we see that electron deficiency is here is high and here is low, that electronegativity difference, so this will form and this will not form. Okay, so that is going to be written here, and this is going to be like this. It means that we will get, and this is going to be like this. Okay, this is the final answers for these questions. Okay, for this will be the final answers. Okay, now moving to the next questions. So for these questions, what you see here, that stereochemistry is mentioned, and remember that this I said about of that single ring. Okay, if in a single ring, now this is not a single ring. Okay, so now you will not apply this formula. This is in a the fused ring. Okay, this is fused ring. Okay, and this is a single ring. So for fused ring, this will not applicable. Okay, for fused ring, what we see here, that this is in the above side. So not that, what we look here, that let's say if any groups, so if it is in the above sides and this is in the planar, this is above side, then this has to be the below side. These two rings will has to be the below side because this is in the above side. So to avoid that steric hindrance, what will do that? This is going to be the below sides, because this is in the above side. To avoid this steric repulsions, this ring will go to the below sides. This ring go to the below sides. So what we see here, that what you see here, that since that one group is in the above side, for the case of fused ring, since this is in the above side, so to avoid the steric hindrance, these two rings will go to the below sides. Two rings will be below side. Okay, because this is already in the above side. So to avoid that repulsions, that will happen. And now here what you get, that CH3 minus is there, and this CH3 minus, what it will do, that it will do that 1,4 conjugate additions. So where it will attack? It will attack to here, because 1 2 3 4 1,4 conjugate additions will happen by the Gilman reagents. Okay, so now it will attack to these positions, but what will be the stereo? So stereo will be that since these two rings go to the below sides, means that in the below side the steric will happen, because two big rings are in the below sides, and in the above side only methyl is there, so it will attack to the above side only, not go by below sides, because compared to these two rings, methyl is the less steric, because this is the two rings. Okay, that will be a bulky compared to this metal, so this will attack to the same side of the stereo. So whenever in a fused ring is there, okay, so whenever in the fused rings, then the incoming group will attack to the same side of that uh, stereochemistry of that whatever that uh, 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 substituent group is there at that junction positions. Okay, so what you say, that if, or I can say that in fused systems, incoming group will be same stereo as the substituent in the substituent present at fused positions. Okay, so that we have to remember from these points. So if it is a fused systems, then that incoming group will attack to the same stereo as that fused ring, that fused substituent. So this substituent is the above, so that incoming group will attack also from the above sides. Okay, so from here what will get that product? So that it will attack to the same side. So here we write like this. So here this is already in this positions, methyl is there, and this methyl also going to be the count like this. Okay, and this is going to be shift here, and this is going to be like this. So this is going to be here, and this is going to be that O minus. Okay, now after hydrolysis what will get here is going to be that O. After hydrolysis that it will shift it to here, and this is going to be like this. So this is because OH bond will not form, because CH bond has also chances to form. So on this case CH bond will form. If there is no chance to form that CH bond, on that case OH bond will happen, but here CH bond also chance is there, so it will form that CH bond. Reason is that there is less electronegativity difference, which will give more stability. Okay, so this is going to be like this, and this is the final answers for these questions. Okay, if this type of questions will ask fused system, then if it is attacking to the fused system, then remember that substituent will, that attack will be the same as that stereo of that fused molecules. Okay, now moving to the next questions. So for these questions, okay, here also what you say that again CH3 minus will be there. Okay, now where it will attack, that it will do always that 1 4 conjugate additions, means that this is 1, this is 2, this is 3, this is 4, so it will attack to here. Okay, so now what we see that if you make it this in the cyclohexanes, then let's say here is double bond is there, and 1 1 2, here we have that methyl groups. So these bulky groups always they will be in the equatorial positions. So this will be again here in this CH3, and 1 1 2 3 3 here again that is there, and that is also has to be present in that equatorial form, because that bulky groups always present in the equatorial positions to avoid that 1 3 diagonal interactions. So here we have these groups 1 sorry 1 2 3 1 2 3 4. So 1 2 3 1 1 2 3 1 2 3 and 4. Okay, so this is also equatorial. So now you are attacking these groups, and this will do that 1 4 conjugate addition. This is 1, this is 2, and this is 3. So 1, here we have this double bonds here. So this will attack to where this will attack to that 1 4 conjugate additions will happen. So 1 4 conjugate addition for that count from here 1 2 3, and this is 4. So this is going to attack to these positions, and this is because here already this group is in that equatorial positions. Now this has to attack, although this is a bulky groups, it will attack to that axial position, because in one carbon center there is two attack will possible, either equatorial or axial. Since already that equatorial positions one group is occupied, so this has to attack that axial positions. Okay, so that it will do that. Here we will not look that 1 3 diagonal interactions, because one is already equatorial, so other has no options to equatorial attack, because equatorial attack is equatorial position is already filled. Okay, so this will come to that these positions. Okay, 1 2 3 4, and that is going to be shifted here, and this is going to get that O minus. Now what we'll do here now, okay, so now what will happen, that O minus is there. Now what we'll do, that this is O and this is has to be written here now. Okay, so now what will happen, that O minus and this is going to be shifted here, and this negative charge here I is there. Okay, so this negative charge will attack to these groups. Okay, so this negative charge what we get here, that now you see here. Okay, so this is going to be double bond O, and here we are getting the negative charge, and here we have these groups 1 2 3 4, and here we have that iodine. This is 4 groups or 5, I think. 2 3 4, I think here 5 was there. 1 2 3 4, 1 2 3 4 5. Okay, so here 1 2, so 1 2 3 4 5, here iodine. Okay, so now what happened, that this I minus will attack to these groups, and this iodine ones will be released. So what that form will form, that again 5-member ring will form here. So see that this is, if you count here from 1 2 3 4 5 6, sorry, this will be the 4 bonds actually mentioned that. So look that questions accordingly we can form that. Actually it is that 5 bonds is there. Okay, so because 5-member ring, 1 2 3 4. Okay, so this is that, and this will attack to here. This is not 6 5 3, this is 1 2 3 1 2 3 4. Iodine was there, so now it will attack to this, and this is going to release here. So how many ring will form? 1 2 3 4, because again 5. Actually that was a 5-member ring was formed actually. Here we have that iodine. Okay, so this will attack to here, and this is going to be released here. So what we will see here, that here 5-member ring will form. Okay, so if I draw here, this is going to be double bond of O, and with this iodines, this 5-member ring will form. 1 2 3 4 5. Okay, and here we have that CH3 group. So if you convert into that original form, then what you will get here, here CH3 was also there. Okay, at the 2 positions, here CH3 also there. Okay, so look that here CH3 also there. Okay, so if you convert into that original form, then what you get here, like this. Let's name it 1 2 3 4 5 and 6. Okay, so 1 we have that this carbonyl groups 1 2 3 4 and 5 and 6. So and at the 2 we have that CH3 is there. With that 2 and 3 will make that 5-member rings. So make that 5-member ring, and what you see, that this is already in that this is comes to the equatorial position, so this will go to that below sides 5-member ring. Okay, 1 2 3 1 2 3 4 5. Okay, this will happen. And at 3 to the 1 2 3. Okay, 3 is that, and here also another 3 is another group is there, that is in the above side. Here is again that CH3 group is there, so this is again going to be that above. Okay, so for that questions, this is the final answer. Check it. Okay, okay, so that depends on that. Yes, so for these questions, if it is a you will look there that if it is a 1 2, how many rings are there, like here 1 2 3 iodine is there. On that case, how many rings is there? 1 2 3. So here 1 2, so on that case 5 member. If 3 or that 6 member, likewise we can form here. So this type will be that final answers for this question. That depend on that how many rings is like this is present. Okay, now moving to the next questions. Okay, for these questions again that same types is asked here. So now this is already a fused system is there. So now what you see that we have to attack here. This is that for organolithiums, that is sorry, Gilman reagents. What type of reagent is there? So that either it may be that the solvents. Let's talk about other solvents. So for that Gilman reagents, that solvent is, and that solvent is, they can ask that same solvent like diethyl ethers, that is ATTO, or we can say that THF. So this type of solvents are taken for the Gilman reagents. Okay, why? Because this will inert to this reagent, Gilman reagent. This will be inerts, and it will give that good facility to the reactions. So what type of solvents you will use for the Gilman reagents? Either we can use the diethyl ethers or THF. Okay, and that conditions will be that the temperature will be taken. Temperature is very low, that is minus 20 degrees centigrade will take for that type of Gilman reagents or Gilman reagents. Okay, so this is that solvents and that conditions are taken for the Gilman reagent. So here that it is mentioned that 82O, so this is the solvent. So they want to confuse you by giving the solvents. Okay, this is the diethyl ethers. Okay, now if you do that, from here what you get, that here we will get that CH3 minus. Okay, and this CH3 minus will do that 1,4 conjugate addition, so it will attack to here, and it is going to like this, and it's going to like this. So what you say that in the fused system, what you say that if attacking to this, the incoming will be that the same as that I have seen in the previous class. But now what you see here, that this already make it. So what I have told you in the previous class, that so if you are attacking to the in this fused cell, on that case we will look that next one. Okay, but now what you see here, that since here and here these two are in the above side, it means that this will be is in the below side. Yes, because this is actually what it shows, that if these are two are in the above side, it means that these two rings are in the below sides. It means that in the below sides, what the two rings are there, and above side two CH3 groups are there. Okay, so now that incoming group will attack where there will be the less hindrance. So compared to this 2CH3, this will be the more bulkier. So it will attack in the above side only. Okay, why? Because this is also in the below side, then these two rings also in the below sides. So this will attack in the same ring as that these fused systems. So that the same things you can say that if in a fused systems, if that rings the substituent groups at the fused, okay, not here, at the fused systems where they are the same stereo, that incoming group will attack. It means that I can say that if it is a fused systems, then look that the substituent at the fused, on that fused, what the substituent is, it means that at the fused the substituent at which stereo they are present, the incoming group will attack the same stereo as that substituent in the fused system. It means that it will attack in that above side, because fused system that is also in the above side. Okay, so the incoming group will attack the same stereo as that substrate which are present in the fused systems. So here it will attack in the below sides. Also, if you are confused with this, make that in the cyclohexanes and do check that. So I think that is not need to check for this case. Okay, because you understand from here that these two are in the below side, means below side is bulkier, so it will attack in the above side. So that is going to be like this. Okay, so that here we have these types of groups here. Here we have that CH3, here also we have that CH3. So this is going to attack in that above side only. Here we have the CH3 and this is going to be like this, and here we have that O minus. Okay, now we did that hydrolysis. It means that it will comes here and it's going to like this. So it means that this will become this groups. This is the final answers for these questions. Okay, here we have that CO2 Me. So this is not a impact here, because this is these rings are below and this is also below, so that will not affect anything. So you will look that the stereo of that substituent which is present at the fuse, not these groups. Okay, so this is the final answers for these questions. Okay, so let me okay, so this is the final answers for these questions. Okay, so moving to the next questions. In these questions, what you see that this is the single systems. Okay, this is not fuse, this is the single systems. Okay, so now what you see that here also you will get that R minus. Okay, and it will attack to the one port, that is 1 2 3 4 1 port, so it will attack here. And what we see that here we will look that next stereo. Okay, so in this case we will look that this stereo, or if you get confused, it simply convert into that chair port, because it actually exists in the chair port. Let's say here we have that double bonds. So let's forget it. This is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So at 1 and this is 1. Okay, this is 2, this is 3, and this is 4. So this is the 5. So 1 2 we have, that is 2 3 we have this double bonds, and this 4 we don't have, and 5 we have that groups that is in the, here we have, this is the above side. Okay, so above side means that is has to be like that groups. So this is present like this. So whatever the mentions, just do that. Okay, same manner. Now what is going to give that CH3 minus we are going to give. So it will do that 1,4 conjugate additions, means it will attack here. Now the question is whether it will attack in this or it will attack. So since this is bulky groups, so it will always attack in the equatorial position. It will never attack in that axial positions, because this is the bulky groups. It means that it will attack in the below sides. Okay, because below side is the equatorial, so it will attack here, and this is going to move here, and this is going to be that O minus. Now we are going to get this, and this is going to be like that. Then what you see here, so if you get confused, then convert into the chair form. It is always correct. Okay, in the chair form this is always correct, and this is going to be that CS3. If you convert into, then what you'll get here, then here double bond of 1 2 3. So at the third position 3 and 4, this is 4 and this is 5. Here we have these groups, so 1 2 3 4 5 and 6. So 1 we have, 2, then 3 we have, that is in the below sides. So this is below sides, and this at the 5 we have at the above side. Okay, so that the same things either we can apply here also. At 2 also we have these groups. Sorry, then it will not happen. Okay, it will attack the below sides, that's the correct. But now here, that what you see, that at 2 positions, here we have this group, that is 1 2 3 4. Okay, 1 2, that is 1 2 3 4, 1 2 3 4, right? 1 2 3 4. Okay, this is there. So what you will see that this will shift here, and this is going to be coming to like this. So what you see here, okay, this is going to be double bond of O, and here we are getting that negative charge, and with that here we have these groups 1 2 3 4, 1 2 3 4 4. Here we have that iodine. Okay, and here we have that CS3, and here we have that groups. Now what you see that I minus will attack to this, and this leaving group will leave. Okay, so this is what we get here. So this is a double bond of O, and here we will make that. So this is 1 2 3 4. So 4 bond will make. Okay, and here we have that CS3, and here we have that this group. It means that if we convert it into that this form, this format, then how will convert here? Okay, so at 1 2 3 4 5 and 6. So 1 we have this, and 2 we have that rings, and this is in the down above, because below is that axial positions. Okay, that bulky groups always present in the equatorial, so this is the above. So above we have that. It means that we can write like this: 1 2 3 4. This is there, and 1 2 and 3 we have this CH3, that is also in the below sides. Okay, and this 4 and 5 we have this close. Okay, so this is the final answers for this type of question, for these questions. Okay, so if you get any confused, like here you have these bonds that is attacking the below side or above sides, if you're getting confused, then make that in the chair form, and this is always answer is correct. Okay, because it is actually exist in this chair form. Okay, this is the for shortcut actually. This one is the shortcut. Okay, so if you want to get that actual answer, then convert into this chair form. Okay, So because what you say that you can simply solve by knowing these things also, that's why I give you shortcut. But if you want to actually solve this, then convert into the chair form. From that you will get these things. Here we want to get that, here we have that Cl, and here 1 2 3, so 1 2 3, here you have the CH3, and this is bulky groups always in the equatorial, and now we are going to attack this CH3. So here the double bond is there, 1 2, here we have double bond, so it will attack where? This is attack in the axial position, because one is already in the uh, uh, equatorial, so that's why it is going to the above. Okay, so this is the shortcut of this. So this is the final answers for these questions. Okay, let me check the answers also. Okay, so that is the answers. Okay, this answer is correct. Okay, so likewise we can solve that questions. So one more problems is left. The last problems for this class, that is if this is given. Okay, so what you say that if you can easily solve by looking this, then you can. So actually I always suggest that best convert into the chair form. Okay, shortcut is fine, but if you solve that chair form, then if you solve like this, then that shortcut is not needed. Okay, here 1 2 3 4 5 and 6, so this double bond over. Okay, 1 2 3, 1 2 and 3, here we have this double bond, and this is 1 2 3, this is 4 and 5 we have, that is above means here this is methyl is there. Now we are going to this LiLH4 we are going to give. So LiLH4, what will go? It will transfer that H minus, and this H minus, this is a strong, so this is hard, so hard will attack, so it will attack to here. Okay, because this is hard and this is soft, so hard will do the interaction, so it will attack to these groups, and this is going to like this. What we are going to get here? Okay, so since this H minus, there is that one for axial interactions is again possible, because here methyl is there. Okay, so 1 2 3, so this H minus will attack in that below sides. Okay, because here methyl is already present, so this is going to, O minus is going to like this, and H will be here. Okay, this is like this, here we have that methyl. Okay, now what we will do that, now next reagent is ACTO. ACTO and pyridine is there. So pyridine is what? That is, it has that it will give that pyridine means this type of groups. There we have that H. So this H will attack to this. Okay, and it is pyridine means. So we know that pyridine is a good base. Okay, so this pyridine will, what it will do, that it will attack to that groups. That is that groups, and okay, so what happened that they do the hydrolysis by itself, and here we'll get that H, and since pyridine is there, then this will accept that base, and again you are getting that here, that negative charge. Okay, so again you are getting the negative charge here. So this negative charge, what it will do, that it will comes to here. After that, what you will going to give, means what they want to say here, that they did the hydrolysis by itself. Now we are giving that pyridine and Ac2O. It means that this pyridine is a base, because pyridine is a base, so it will obstruct this H, and here we are getting the negative charge. So what we get here, so this is going to be that O minus, and here we have that H already, here double bond, here we have that methyl. Okay, now we are going to give that Ac2O. Ac2O means this is acetyl CH3CO, O, CO, CH3. Okay, so this will attack to these groups, and this is going to be like this, and this is going to be like this. So what you see here, here we have O and COCH3, and here we have that H. Okay, now here we have the double bond, and here have that methyl. Now what they want to give, they now going to give that Gilman reagent, that is Me2Culi, that is going to give that CH3 minus. So this Me2Culi, yes. So this is going to attack. So this is the double bond here. So this is going to attack this 1,4 conjugate additions. So what it will do, that it will attack to these groups, and this is going to shift here, and this is going to be a good leaving group, so this is going to leave here. So now since if it is attack 1, 2, 3, again that 1, 3 diagonal interactions is possible, so this is again attack in the axial position, so that is going to leave here, and this is going to double bond over here, and this is attack again in the below sides, CH3. This is the methyl. So if you look that made to that form, then what we are going to get this, and here we have that, let's say this is 1, I'm taking this as 1, this is 1, this is 2, this is 3, this is 4, this is 5, 6. So 1 and 2, this is 1, 2, 3, 4, 5, 6. So 1, 2 has double bond, and 3 you have that CH3, that is in the below sides, CH3 at the below sides, and 4 and 5 here, that methyl is in the above side. Okay, so for this is the final answers for these questions. Okay, this will happen here, means one CH3 is above, another CH in the below sides. Okay, so this is the final answer for these questions. Okay, so practice more, we will clear more that type. Actually for this question, first convert into chair form, then we will attack it. Okay, so today after this we will discuss more in the next class. Thank you.